Good morning, everyone. My name is Yihan Xu from NTU Singapore. Today, I'm going to introduce our work, Hyper 3DEF. It is a defense method aimed at protecting the Car-Borne vehicle LiDAR detection system from the adversarial attacks. Now, let's start with some background information. LiDAR has been identified a key sensor in autonomous vehicles because it can provide direct depth perception and precise bounding box of the object. It also enables the perception under low light conditions, such as at night. For these reasons, mechanical LiDAR with full FOV and high resolution is first adopted in industrial vehicles. Nowadays, the low-cost and compact semi-solid-state LiDAR is more popular in the passenger vehicles. However, the LiDAR detection system is vulnerable to physical attacks. Both the LiDAR sensor and the 3D detection model, which use a point cloud input and output bounding boxes, can be the attack targets. If the sensor information of the LiDAR is leaked, the attacker can use electromagnetic signals to negatively affect the LiDAR. And when the information of the model is leaked, he can use real objects to add physical perturbations in the clean frame and create adversarial examples to mislead the LiDAR. There are basically two types of attacks. The first is black box attack to query the model outputs. And the second is a white box attack, which optimizes the perturbations based on gradient computing. In this project, we focus on defending the adversarial attacks. In this work, we consider two attack goals, the hiding attack and the creating attack, which are also the mainstream in the literature. Both of them place some attack perturbations along the road to hide an existing vehicle from the detection result, or to create a fake vehicle in front of the victim vehicle. These attacks may cause severe consequences. In the hiding attack, the victim vehicle may crash into the front vehicle. And in the creating attack, the victim vehicle may suddenly brake and be hit by the vehicle behind. For each type of attack, there have been some useful defenses. For example, searching the positions of the perturbations and remove them is effective in defending the hiding attack. And for creating attack, checking a detected bounding box if it has a reasonable shadow in the point cloud map is useful. However, these defenses have a major limitation. They are vulnerable to adaptive attacks, which allow the attacker to obtain the information of the current defense and construct the next effective attack. For example, if the current defense is designed for the hiding attack, the attacker can choose a creating attack and bypass the defense system. Our objective is to develop a useful defense which can be against the adaptive attacks. So far, I have presented the information of the background and our objective. Now I'm going to present the dynamic defense. The basic idea of the dynamic defense is that the adversarial attack is very hard to transfer across different model parameters. For example, now the attacker uses the parameters of M0 to construct an adversarial frame and test this frame with model M0 and M1. M1 and M0 have the same structure, but they are separately trained from the scratch. The result is that the attack frame successfully misleads M0, but it is less effective in misleading the M1. Based on this, existing defense decides to use a hypernetwork, which can produce new parameters from the noise lantern code decided by a random seed. In any time step, this hypernetwork can generate multiple models and form an ensemble. The ensemble will process the input figure and vote to a final classification result. The whole process can be repeated with a fixed time interval. This is hard for the attacker to attack this system because if he wants to successfully disable this system, he needs access to the current ensemble information and also additional time costs to construct and deploy the physical attacks in real world. This can be hardly finished during 2 time steps because the update frequency of this system is very high. However, when we want to apply the HyperNet-based defense in LiDAR detection system, we will face 3 challenges. The first challenge, the 3D detector is much larger and more complex to the 2D classifier, so the HyperNetwork is unable to generate a whole model. Second, different from the voting for classification labels, detection results are multiple bounding boxes with continuous parameters. There will be also some disturbing options, so how to fuse them is a question. The third challenge is that the 3D detector model is much slower, and an ensemble of 3D detector models will bring high time cost. How to reduce the time cost is a problem. To solve these 3 challenges, we propose our method, Hyper3Dev. Let's look at the detailed design. To solve the first problem, that the HyperNetwork has limited generation capability. Our solution is to only select several layers to be generated, while keep the other parameters frozen. But which layers to be generated can maximize the defense effectiveness? First, we give 2 observations. We need to control the number of parameters generated to balance the 2 factors, the defense effectiveness and the clean accuracy. They are conflict goals. If we generate too many layers, the defense may be strong, but we will get a relatively low accuracy. Secondly, generating and replacement on the shallow layers is more effective in defending compared to the same operation on the deep layers. Because the shallow layers can process the input feature earlier, and the change on the feature map can be accumulated by subsequent layers. In this work, we design our system on a base model, the point pillars, which is also a widely adopted 3D detection model in both industrial and research area. Since most of the parameters are concentrated on the convolution backbone, we decide to replace several layers of the backbone and combine with the observations above. Our final strategy is to replace 6 layers of all the layers, which can be also represented as the purple blocks in the right figure. With this strategy, we can achieve the best defense performance while keep a relatively acceptable accuracy. To further enhance the defense performance, we also need to increase the model diversity, because model diversity measures how the models respond differently to the same attack example. We have 2 major designs. First, we add a new similarity loss in the training phase, which is based on the parameters generated of every member in the ensemble. With this loss, we can push our HyperNetwork to generate more diverse models. Second, we observe that in the routine training for a single model, if we use the same inputs, the model will be similar. And if we use the different input data, the models will be diverse. So we decide to separately augment the raw frame and phase them into every member of the ensemble specifically. We have multiple operations, and in each operations, for example, like rotation, we will randomly apply different rotation angles. The whole process can also be considering creating a customized data set for every member. Now we have many diverse models, and they can produce detection results. So how to fuse them? We will first stack all the bounding boxes into the bird view plane and separate them into different clusters. Only in the large cluster, passing the threshold checking will be kept. Otherwise, it will be discarded. Inside every cluster kept, we will use 2 branches to fusion to get the final result. In the first direction fusion, we will use majority voting and averaging to get a final direction angle. And in the second branch, we will directly fuse the other parameters, such as the dimensions and positions. Finally, we combine the 2 results and get a box. Previously, we mentioned that to pursue the defense effectiveness, some clean accuracy of the ensemble results will be sacrificed. So we decide to use the result from the original model to calibrate the ensemble result, while keep the security. The whole calibration process can be presented in the left pseudocode. For every box from the ensemble, if it is correctly matched with any box in the original result, we will use the original box. Otherwise, we will still use a box from the ensemble result. In the right table, we show the effects of our calibration. For example, if the input frame is clean, both the ensemble and the original model are very likely to detect the correct bounding box of a real vehicle. After successful matching, the final box will be the box from the original result, because we have a pre-knowledge that it has a higher clean accuracy. When the input frame is a hiding attack, the original model is very likely to miss the result, and our ensemble are very likely to detect it. So the final result, we will directly use the box from the ensemble result. And for the creating attack, the ensemble result is very likely to identify there is actually no box of this vehicle. So there's nothing to calibrate. The final result will be no box. In conclusion, we use a calibration to preserve the clean accuracy while keep the security of the system. Remember that in the third challenge, we mentioned that an ensemble of the 3D detector models would bring a very high time cost. So how to reduce it? We design and integrate a new attack detector with the original Hyper-3DEF to produce the Hyper-3DEF Plus. The attack detector would decide whether it will raise the alarm based on the input frame. If yes, we will execute Hyper-3DEF to process the input frame. Otherwise, we will only run the original model. Basically, only the adversary examples will trigger the alarm. This figure shows the effects of our design. Compared to Hyper-3DEF, Hyper-3DEF Plus, in the clean case, can cost only half of the time. We have implemented Hyper-3DEF and Hyper-3DEF Plus in both real-world and simulation experiments. The metric we use to evaluate the defense is attack success rate, which can be defined as the ratio of the number of success frames to the number of total frames. In our attack design, a certain victim vehicle with a LiDAR is moving towards a static vehicle with some objects around. The position of the objects are determined by existing algorithm to hide the static vehicle. With no defense, this attacker can achieve 90% ASR in continuous frames along a 10 meters road. After the deployment of our defense, we can reduce the ASR to 5%. Apart from the real-world experiments, we also do some simulations to test our defense in more complex and diverse driving scenarios. The baseline method for comparison includes adversarial training, static ensemble, and so on. For Hyper-3DEF, both the hypernetwork itself and the historical models can be linked to the attacker. But the random seed is not, because it can be nearly impossible for the attacker to precisely synchronize with the driving system. The right figure shows the defense performance of method. Compared to the best baseline, our method can reduce the ASI by 50%. In conclusion, in this project, we propose a dynamic defense against adaptive attacks. We show the limitation of current defense against adaptive attacks, and we are the first dynamic defense in LiDAR object detection. We also integrate a LiDAR video attack detector to reduce the time cost. Thanks for listening. Very happy to listen to your questions.
Any questions?
Okay, very interesting work and great presentation. This is Leming from Hong Kong Poly. And my question is that have you ever tried any other ensemble methods such as fusion-based, feature-based fusion instead of voting?
In this paper, we do not apply the feature-based fusion. We directly use the voting. It is an interesting attempt that we can use it in the later work to test the defense.
Okay, I see. And another question is, have you varied the threshold of choosing your model and the original model to see its influence on the defense success rate? Yeah.
You mean in the calibration?
Yeah.
Yes. So in our paper, we give a sensitivity study of the. So it is this page. Yes, we give a sensitive study about changing the threshold in the matching. So based on our experiments, there's a wide range from the 0 to 0.8. We will all give a very good result in keeping the clean accuracy and security. But if we select the threshold to be more than 0.8, the result will be awful. So we do not apply that.
Okay, I see. Very interesting. Okay, thank you.
Hello, Miles from UC Irvine. Thank you for the interesting talk. So I wonder, for these kind of attacks, just out of my curiosity, is it possible to come up with some really simple deterministic-based approaches to act as a last layer defense whenever those models fail or getting attacked?
Do you mean that there's some physical characteristics about the attack, so we can use these characteristics to defend it?
It's something like that. So like by being deterministic mean that maybe you can just do some simple checks with the raw LiDAR data to see.
This is a very cool question. So yes, in fact, it can be. So yes, for example, in the creating attack, we mentioned that a real vehicle has a corresponding real shadow in the point cloud map. So we can check that if it has a shadow to identify whether it is a real vehicle, right? So it is an effective defense. But in this paper, we want to address that the attacker now knows that your defense is designed for process the creating attack. It is very successful. So I do not use a creating attack to test your defense because it can be hardly successful. We will directly choose another attack types such as hiding attack to bypass the defense system. Yes, this is what we want to address in this project. Thank you.
Okay, thank you. Maybe we can talk a little bit more.
Okay.
Thank you.
Yeah, I can shoot a follow-up on that. So I don't know if you know, there's a significant crunch on onboard compute resources in the industry. Even all the models now are quantized, or all the tricks apply to make it more efficient in terms of resource usage. Do you think, I just want to get your thoughts on how can model assembling be implemented in the current situations? Or do you have any thoughts on that?
Yes. In this page, we show some results about the time cost of our method. So all the methods are based on are running on an embedding device like our ring. So we miss the result of the single detection model without any defense, without our defense, without any type of defense. So it costs about 80 milliseconds. So you can see that hyper-3 depth, it costs 248 successors. So it is a bit larger. So with our design, the hyper-3 depth plane, we can reduce it to 132. It still costs sometimes because, but we can continue to optimize it. Okay.
Right, but in the case that there is a detection of the attack, you have to run multiple models. Right?
Yes, yes.
And what if there's no resource allocated to those extra models?
You mean we detect that there's an attack, but now they have different. So we can choose some parameters dynamically to further. Before you can see that now we use 4 models, in sample size close to 4. We get this result. But to sacrifice some of the defense performance, we can reduce sample size to 3 to even 1. It also shows some defense ability to the straight restrictions.
Okay, thank you. All right, let's thank the speaker again.